Have you ever stopped to think about why absolutely nothing in the universe can stay completely still? Right now, as you watch this video, you are spinning at over 1,000 miles per hour along with the Earth, which is orbiting the Sun at an incredible 107,000 miles per hour, which in turn is spinning around the center of the Milky Way at 528,000 miles per hour. And our entire galaxy is hurtling through space at over 2 million miles per hour toward the Virgo cluster. And all this while the universe itself is expanding at speeds that defy our understanding. Then the question that astrophysicist Neil deGrasse Tyson so provocatively asked, and that will guide our journey today, is simply disturbing. Why on earth can nothing stay still in the cosmos? The answer goes far beyond what you imagine and has its roots in something that happened 13.8 billion years ago, in the violent and chaotic birth of the universe itself. And when you understand the physics behind it, your perception of reality will never be the same. Neil deGrasse Tyson often says that motion is the fundamental signature of the cosmos, the one universal constant that permeates everything from subatomic particles to galactic superclusters. And this seemingly simple statement hides one of the most profound and beautiful truths about the nature of physical reality. Imagine if you could somehow freeze the entire universe right now, stop any and all movement of every atom, every planet, every star, every galaxy. What would happen? Physics tells us that this would be literally impossible. Not just improbable or extremely difficult, but fundamentally prohibited by the laws that govern existence. And if you are one of those who love unraveling the mysteries of the cosmos like I do, subscribe to the channel because we have many more fascinating scientific revelations about the fundamental nature of reality to share with you. The question of perpetual motion in the universe takes us straight to one of the most elegant and powerful concepts in all of physics: angular momentum. And understanding this is like being handed a master key that opens the door to understanding everything from why skaters spin faster when they shrug their arms to why spiral galaxies have that majestic, mesmerizing shape. But before we dive into deep physics, we need to go back to the absolute beginning of it all, to the moment when time and space themselves were born in an explosion of energy so incomprehensible that to this day, physicists struggle to mathematically describe what happened in the first trillionths of a second after the Big Bang. In the beginning, there were something cosmologists call quantum fluctuations in the vacuum, tiny microscopic irregularities in the distribution of energy and matter that appeared and disappeared in the fabric of primordial space-time. And these tiny fluctuations, smaller than an atom, carried with them tiny random rotations, tiny whirlpools of energy that spun in chaotic and seemingly meaningless directions. When the universe burst into existence 13.8 billion years ago, these fluctuations were magnified dramatically by cosmic inflation, a period of exponential expansion so violent that the universe doubled in size at least 60 times in the tiniest fraction of a second you can imagine. And along with the matter and energy being stretched across the nascent cosmos, those little whirlpools of rotation were also magnified, spread across galactic distances, preserved as permanent scars in the fabric of space-time. Neil deGrasse Tyson explains this brilliantly when he says that the universe was born already dancing, already spinning, already in frenetic movement from the first moment of its existence, and this initial movement never stopped, never significantly slowed down, because there is nothing in the vacuum of space to slow it down. No cosmic friction that could slow down the eternal waltz of the galaxies. For the first 380,000 years after the Big Bang, the universe was a dense, opaque soup of superheated plasma, where protons, electrons, and photons constantly collided at temperatures of millions of degrees. But even in this primordial chaos, angular momentum was being preserved, the initial rotations being passed from particle to particle like an inerasable cosmic inheritance. As the universe cooled and expanded, something extraordinary began to happen. Gravity began to pull matter together to form the first structures, clouds of hydrogen and helium that would eventually become the first galaxies. And here is where the magic of physics really manifests itself in spectacular fashion. When a gas cloud in space begins to collapse under its own gravity, any microscopic rotation it possesses, no matter how small, will be drastically amplified as the cloud shrinks, by exactly the same principle that makes a skater spin faster when she pulls her arms closer to her body. And this fundamental physical principle is called conservation of angular momentum. Angular momentum is a physical quantity that describes how much something is spinning. And the law of conservation says that in an isolated system, the total angular momentum never changes. It is eternally preserved as a kind of physical memory of the universe that cannot be erased. Imagine a cloud of interstellar gas 100 light-years in diameter spinning lazily, making perhaps one complete rotation every billion years, a rotation so slow that it would be imperceptible even if you could observe it for millions of years. But then, gravity starts to pull that cloud inward, compressing it, and as its size shrinks from 100 light-years to 10 light-years, then to a light-year, then trillions of kilometers, the speed of rotation increases exponentially, like water spinning faster and faster as it approaches the drain. When this cloud finally collapses to form a galaxy about 100,000 light-years across, it is spinning so fast that it only takes a few 100 million years to complete one rotation. And the stars on the outer edge are moving at hundreds of kilometers per second, creating those majestic spirals we see in galaxies like Andromeda and our own Milky Way. Neil deGrasse Tyson likes to emphasize that it is no coincidence that almost all the galaxies we observe are rotating. This is not a cosmic accident or a quirk of nature, but an inevitable and mathematically guaranteed consequence of the fundamental laws of physics combined with the chaotic initial conditions of the Big Bang. Within these rotating galaxies, the same process repeats itself on smaller scales. Clouds of gas and dust within the galaxy begin to collapse to form individual stars. And again, any microscopic rotation these smaller clouds possess will be amplified dramatically as they shrink. A cloud of gas that will eventually form a star system like our solar system may start out tens of light-years across, rotating so slowly that it would be impossible to detect. But as it collapses over millions of years, this rotation intensifies until at its center forms a rapidly spinning baby star, and around it, a flat disk of rotating material from which planets, moons, asteroids, and comets will eventually be born. And this discovery that I'm sharing with you impacted scientists around the world when they finally understood that the shape of planetary systems is not random. So comment in your city or country. It's incredible to think that we are all connected in this same rotating universe, trying to understand it better. Because the reason why our solar system is flat, like a disk, and not spherical like a ball, is precisely because of the conservation of angular momentum. When that primordial cloud that formed our sun began to collapse 4.6 billion years ago, it had a net rotation in a particular direction, say clockwise from above. And as the cloud shrank, matter tried to spin faster and faster. But there was a physical problem. Matter can't just spin infinitely fast without starting to spread outward due to centrifugal force. Along the axis of rotation, from the North Pole to the South Pole of the cloud, matter could freely collapse toward the center because there was no rotation in that direction. But in the equatorial plane, perpendicular to the axis of rotation, the collapsing matter had to compete against the centrifugal force created by the rotation itself. And the result was that the cloud flattened into a disk, where all the matter rotates in the same direction around a bright central star. This is why the planets in the solar system all orbit the sun in approximately the same plane. This is why they all orbit in the same direction. This is why most planets rotate around their own axes in the same direction as they orbit the Sun, except for a few exceptional cases like Venus and Uranus, which suffered cataclysmic collisions that altered their rotations. And this is why Saturn's rings are flat and not spherical. But here's where the story gets even more fascinating and where Neil deGrasse Tyson really shines in his explanations. Rotational motion is not just preserved on galactic and stellar scales. It permeates absolutely everything down to the smallest scales we can imagine. Take Earth, for example. Our planet rotates on its axis once every 23 hours and 56 minutes, completing a full rotation that creates the day and night cycle that governs life on the surface. And this rotation causes someone at the equator to be moving at approximately 1,670 kilometers per hour due east, although you feel absolutely nothing because everything around you, the air, the buildings, the trees, is also moving at the same speed. The Earth's rotation is not uniform from pole to equator. If you are at the equator, you are spinning much faster in terms of linear speed than someone near the poles, because you have to travel a much greater distance in 24 hours to complete the circle. But in terms of angular speed, everyone completes one rotation in the same time. Now, where did this rotation of the Earth come from? It is a direct legacy of that primordial cloud of gas and dust that collapsed to form the solar system billions of years ago. When dust particles and rocks began to clump together under gravity to form protoplanets, each collision added or subtracted angular momentum depending on the direction and angle of the impact. And the net result of trillions and trillions of such collisions over millions of years was a planet spinning in a particular direction at a particular speed. And here's something absolutely mind-blowing that will blow your mind. This rotation is slowing down, but so slowly that you would never notice it in your entire life. The Moon is stealing angular momentum from the Earth through the tides. And as a result, our day is getting longer at the rate of approximately 1.8 milliseconds per century, which means that when dinosaurs roamed the Earth 65 million years ago, a day was only about 23 hours long. And if you could travel billions of years into the future, would find the Earth rotating so slowly that a day would last the equivalent of 47 of our current days, at which point the Earth and the Moon will be gravitationally locked, always showing the same face to each other, exactly as the Moon already does to us today. But angular momentum stolen from Earth doesn't simply disappear into the vacuum of space. Because conservation is an inviolable law of the universe, so where does that angular momentum go? It is transferred into the Moon's orbit, causing our natural satellite to slowly move away from Earth at a rate of approximately 3.8 centimeters per year, a tiny but measurable amount that scientists accurately confirm by using mirrors left on the lunar surface from the Apollo missions, shooting lasers from Earth, and measuring the time it takes for the light to return. Neil deGrasse. Tyson loves using this example because it perfectly demonstrates how angular momentum is a universal currency in the cosmos. It can be transferred from one object to another. It can change shape. It can be redistributed, but it can never be created out of nothing nor destroyed completely. It is a conservation as fundamental as the conservation of energy. And together these laws dictate practically everything that happens in the physical universe. Think about Saturn's rings for a moment, those dazzling bands of ice and rock that surround the giant planet in a disk so thin that if you could compress it while maintaining its diameter, it would only be a few tens of meters thick, despite being hundreds of thousands of kilometers wide. Why are they so perfectly flat? Angular momentum, every particle of ice in the rings is in orbit around Saturn, and all of those orbits are aligned in the same plane because any particle that tried to orbit at a different angle would eventually collide with other particles, exchange angular momentum through those collisions, and end up being forced back into the common plane where all the orbits are aligned. It's like a system that naturally finds its lowest energy, highest order state through billions and billions of tiny adjustments over millions of years. Let's now scale up our view and look at something even more impressive. Entire galaxies colliding and merging, a process that is happening right now in many places in the observable universe. When two spiral galaxies come closer together due to mutual gravitational attraction, each carrying its own angular momentum from its own formation history, what happens is a cosmic dance of unimaginable complexity that unfolds over hundreds of millions of years. The galaxies slowly approach each other. Their shapes begin to distort by their mutual gravity. Long swaths of stars are ripped off and thrown into intergalactic space like luminous bridges between the two cosmic titans. And eventually the two galaxies merge into a single chaotic and turbulent structure. What happens to the angular momentum in this violent process? It is redistributed, partially preserved in the rotation of the new merged galaxy, partially transferred to individual stars that are ejected into strange orbits, partially dissipated in density waves that they course through the new galactic structure like ripples in a cosmic lake. But the total amount of angular momentum in the system remains absolutely constant. It is just reorganized in increasingly complex and chaotic ways. Our own Milky Way is currently in the process of devouring several smaller dwarf galaxies, literally tearing them to pieces with its superior gravity and scattering their stars throughout our larger galaxy. And each of these dwarf galaxies contributes its own angular momentum to the total system, adding small perturbations and asymmetries to the orderly rotation of our spiral galaxy. And in approximately 4 billion years, something absolutely spectacular will happen. The Milky Way will collide head-on with the Andromeda Galaxy, our cosmic neighbor that is currently approaching us at about 110 kilometers per second. And when these two giant spirals meet, their angular momentum will combine in a way that astrophysicists can simulate on computers, but that no one has ever witnessed directly, likely creating the giant elliptical galaxy that astronomers have already dubbed affectionately from Lactomeda or Milkdromeda. If these discoveries about the fundamental spinning nature of the cosmos are expanding your mind as much as they have expanded mine, please like this video, subscribe to the channel, and turn on notifications because we have many more revelations about the deep mysteries of the universe to explore together in the coming weeks. But now we need to dive even deeper and ask a question that may seem obvious, but whose answer reveals surprising layers of complexity. If everything is spinning, is there some absolute frame of reference in the universe, some vantage point from which we could say something is truly still or truly moving? Einstein's relativity tells us that there is no such thing as absolute rest or absolute motion. All motion is relative to some observer or frame of reference. You may be stationary relative to your chair, but moving at 1,000 miles per hour relative to the center of the Earth. You are stationary relative to the Earth, but moving at 107,000 miles per hour relative to the Sun, and so on up the cosmic hierarchy. Neil deGrasse Tyson likes to illustrate this by asking people to imagine that they are floating in the absolute vacuum of intergalactic space, far from any star or galaxy, with no visual reference around them. In such a situation, could you say that you are standing still? The disturbing answer is no. You would have absolutely no way of determining whether you are stationary or moving at super high speeds, because motion only has meaning when measured in relation to something. And without external references, the very concept of motion becomes meaningless. You could be spinning wildly or perfectly still, and there would be no physical experiment you could do to distinguish between these possibilities. But there is a fascinating exception to this rule, a way in which you could detect rotation even in absolute emptiness with no external references. And this brings us to one of the most famous thought experiments in the history of physics, proposed by Isaac Newton more than 300 years ago. the rotating bucket. Imagine that you are floating in empty space, holding a bucket full of water. You begin to rotate the bucket around its vertical axis and observe what happens to the water. Initially, the bucket rotates, but the water remains relatively stationary because it has not yet been dragged by friction with the walls of the bucket. But gradually the friction begins to drag the water along with the bucket until eventually both the bucket and the water are rotating together at the same speed. And then you observe something remarkable. The surface of the water curves, forming a paraboloid concave, higher at the edges than in the center, rising up the walls of the bucket due to centrifugal force. The profound question Newton asked was, relative to what is the water rotating to produce this curvature? It can't be relative to the bucket, because both the water and the bucket are rotating together at the same speed, so there is no relative motion between them, but still the water clearly shows the effects of rotation through its curved surface, so it must be rotating relative to something more fundamental. Newton concluded that water was rotating with respect to absolute space, a kind of fixed, unchanging stage against which all motion could be measured. But this idea always bothered physicists and philosophers because Newton's absolute space seemed to be something that existed but couldn't be detected directly. You could only infer its existence through the effects of rotation. Centuries later, Einstein completely reformulated these ideas with general relativity, suggesting that rotation is not measured relative to a mystical absolute space, but relative to the distribution of all matter and energy in the universe, a concept called Mach's principle, after the philosopher and physicist Ernst Mach. The idea is that if you could somehow remove all matter from the universe except you and your bucket of water, the very notion of rotation would lose meaning because there would be nothing relative to which you could rotate. But as long as there is matter distributed throughout the cosmos, that matter collectively defines a benchmark against which rotation can be measured. Here's where things get truly mind-blowing. This means that when you spin in your chair, you are technically spinning relative to all the stars and galaxies and matter in the observable universe. Your rotation is measured against the cosmic radiation background, against the clusters of galaxies billions of light-years away, against the large-scale structure of the cosmos itself. And this is one of the most profound and poetic ideas in all of physics, that you and the distant universe are intimately connected, inescapable through the geometry of space-time. Neil deGrasse Tyson often mentions that this connection between the local and the cosmic is one of the reasons why physics is so beautiful, because it reveals that we are not separate from the universe by observing it from the outside, but are an integral part of it. Our existence, our movements, even our thoughts are all intertwined with the fundamental structure of the cosmos in ways that we are only beginning to understand. But let's get back to the original question that started this whole journey. Why can't anything in the universe stay still? Now you can see that the answer is multiple layers deep. At the most fundamental level, nothing can stand still, because the very concept of still has no absolute meaning. You can only be still in relation to something, and no matter which frame of reference you choose, there will always be another frame of reference in which you are moving. But there is an even deeper reason rooted in quantum mechanics that adds another layer of impossibility to the idea of absolute rest. The Heisenberg uncertainty principle tells us that you cannot simultaneously know with perfect precision both the position and the momentum of a particle. If you try to pinpoint exactly where a particle is by confining it to a very small region of space, you automatically increase the uncertainty in its momentum, which means it must be moving with some non-zero speed. And if you try to measure its momentum precisely perfect, you lose information about your exact position. This means that at the fundamental quantum level, particles can never truly be at rest. They must always have some residual motion called zero-point energy. Even in the lowest possible energy state, that a quantum system can occupy, called the ground state, there is still motion and fluctuations. The vacuum of space is not an empty nothingness, but teems with virtual particles appearing and disappearing, quantum fields oscillating, a quantum foam of frantic activity on scales smaller than atoms. So in a sense, motion is not just common in the universe, it is absolutely fundamental and inescapable at all levels of reality. From microscopic quantum fluctuations to the rotations of galactic superclusters spanning billions of light-years. The cosmos is a symphony of perpetual motion playing on all scales simultaneously. And there's more. Space itself is moving, expanding since the Big Bang, so that distant galaxies are moving away from us at speeds that increase with distance. Galaxies billions of light-years away are moving away faster than the speed of light, not because they are moving through space, but because the space itself between us and them is expanding, creating more distance with each passing moment. This expansion is not a movement through space, but a movement of space itself, a subtle but profoundly important distinction. And it means that even if you could somehow stop all movement of all matter in the universe, the very fabric of the cosmos would keep stretching, keep growing, keep moving everything further apart in a very real sense. The entire universe is moving towards an increasingly diffuse and cold future, where galaxies will be so far apart that their lights can never reach each other. Now think about what this all means for our everyday existence. You're sitting there watching this video, thinking you're standing still, but in fact, you are part of a dizzying hierarchy of layered movements. Your atoms are vibrating with thermal energy, electrons are orbiting atomic nuclei at significant fractions of the speed of light. Molecules are rotating and so on. Oscillating in chaotic patterns, your body is rotating with the Earth at over 1,000 kilometers per hour. The Earth is orbiting the Sun at more than 100,000 kilometers per hour. The solar system is orbiting the galactic center at almost 1,000,000 kilometers per hour. The Milky Way is falling towards the Virgo cluster at more than 2,000,000 kilometers per hour. And all this while the universe expands, carrying everything away at increasing speeds. You are a cosmic traveler on the move, perpetual. Whether you realize it or not, your journey through space and time never stops for a single instant, from the moment you were born until the moment you die. And here's something that will make you think. In the entire history of the universe, from the Big Bang almost 14 billion years ago to this present moment, you have never occupied the same position in space twice. Every second of your life takes you to a region of the cosmos that never existed before and never will exist again. Because as the Earth rotates and orbits, the Sun moves through the galaxy, and the galaxy moves through the expanding universe, you are tracing a complex spiral through space-time that is absolutely unique and unrepeatable. Your personal trajectory through the cosmos is a curve that has never been traversed before and will never be traversed again by anything else in existence. Neil deGrasse Tyson likes to emphasize that when you truly internalize this truth, when you truly feel in your core that you are a cosmic traveler in eternal motion through an expanding and rotating universe, it fundamentally changes how you see yourself and your place in the cosmos. You are not separate from the universe watching from the outside. You are the universe experiencing itself. You are a temporary form that matter and energy have taken in this particular region of space-time. And when your form dissolves, the atoms that make up your body will continue its cosmic journey, perhaps becoming part of other stars, other planets, perhaps even other life forms in futures so distant that our minds can barely comprehend them. But now let's address a question that may have been bothering you since the beginning of this video. If everything is in perpetual motion, if nothing can truly stop, where does the energy come from to keep all this movement happening forever? Doesn't this violate the second law of thermodynamics, which says that entropy always increases and isolated systems tend toward maximum disorder? The answer is both reassuring and deeply melancholy, because although the motion itself is perpetual, the energy available to do useful work is constantly being degraded and dissipated, converted from orderly forms of energy into diffuse heat that cannot be recovered. Sky high, others losing energy and falling towards the galactic center, and the kinetic energy lost by falling stars is partially converted into thermal radiation that escapes into intergalactic space and can never be recovered. So, although the galaxy continues to spin, it is slowly losing structure, losing coherence, losing the ability to do interesting things with its energy. The same happens with planetary systems. The planets will continue to orbit their stars for billions of years, but subtle gravitational interactions, tidal effects, occasional collisions with comets and asteroids all slowly drain energy from the system. Some planets may eventually be ejected into chaotic orbits. Others may crash into their stars, and the energy lost in the process is dispersed as radiation that travels to infinity and never returns. And the stars themselves, those nuclear furnaces that light the cosmos, are constantly converting mass into energy through nuclear fusion. But this energy is radiated out into space as light and heat that scatters, dilutes, becomes less and less concentrated as it moves away from the source, eventually becoming so diffuse that it is indistinguishable from the thermal background of the universe. Each star is like a burning candle, lighting the darkness for a time but inevitably using up its fuel and going dark. The ultimate fate of all this, if the laws of physics as we know it continue to apply over the next few years, is something cosmologists call the heat death of the universe, a state where all usable energy has been dissipated evenly, where there are no longer temperature differences to produce work, where black holes have evaporated through Hawking radiation, where even protons may have decayed into diffuse radiation, and all that's left is a cold, approaching void. From absolute zero, but never quite reaching it, with occasional particles separated by distances greater than entire universes today. But even in this state of heat death, motion does not stop completely. Individual particles will still be moving. Quantum fluctuations will still be happening. Space itself may still be expanding, even though there is nothing significant in it to observe that expansion, motion, is truly eternal, even when all interesting structure disappears. And there is something deeply poetic about this, that motion survives even the death of the universe itself. But let's not end on gloom. Because although the ultimate fate of everything is scattering and darkness on unimaginable timescales, in this present moment, the universe is alive with movement, structure, complexity, and beauty. Galaxies are still forming stars. Stars are still forming planets. Planets still harbor life, at least in one case that we know of and possibly in countless others that we have not yet discovered. And all this wealth of phenomena, all this diversity of structures from atoms to superclusters exists because the universe has not yet reached thermal equilibrium. There is still energy gradients, there are still asymmetries, there is still structure inherited from quantum fluctuations in the Big Bang and amplified by cosmic inflation. Do you want to know something absolutely incredible about your own existence? The fact that you are alive, conscious, able to ask the question, why does nothing stand still in the universe, is itself a direct consequence of the perpetual motion of the cosmos. Life as we know it requires constant flow of energy. It requires a thermodynamic imbalance where high-quality energy enters the system in the form of sunlight, and low-quality energy leaves in the form of infrared heat. Without this constant flow, without this perpetual movement of energy through living systems, life could not exist. You are literally a localized manifestation of universal movement, a temporary maelstrom of organized complexity sustained by the eternal flow of energy through the cosmos. Neil deGrasse Tyson sums it up beautifully when he says that we are all made of stardust. But we can add to this: we are stardust in perpetual motion, inheritors of angular momentum that began to exist in the first moments after the Big Bang, and was passed down through generations of stars, through the formation of our solar system, through the accretion of the Earth, through billions of years of cosmic evolution, until it reaches you, sitting there right now experiencing the wonder of existing in an eternally moving universe. So, to definitively answer the question that started our journey, why does nothing in the universe stand still? First, because the very concept of still is relative and not absolute. You can only be still relative to something, and no matter which frame of reference you choose, there is always another in which you are moving. Second, because angular momentum is universally conserved, and any initial rotation, no matter how small, is preserved and often amplified throughout cosmic time. Third, because the quantum uncertainty principle fundamentally prohibits absolute rest even at the level of subatomic particles. Fourth, because space itself is becoming expanding, taking everything with it in a movement that cannot be stopped. And fifth, because the universe was born in chaotic movement in the Big Bang, and this initial movement was permanently recorded in the structure of the cosmos as an indelible signature of our violent origin. Movement is not an aberration or cosmic accident. It is the fundamental and inevitable condition of physical existence. It is as basic as time and space, as fundamental as energy and matter. And to understand this is to understand something profound about the nature of reality itself. And as you process all of this we've explored together, as your mind expands to encompass these cosmic truths about perpetual motion and conservation of angular momentum, about quantum fluctuations and the expansion of space-time, about the eternal dance of galaxies and the silent waltz of particles in a vacuum, I hope you feel the same sense of wonder that astrophysicists like Neil deGrasse Tyson feel when they contemplate these questions. Science does not take away the magic of the universe. It reveals even deeper layers of magnificence that our everyday intuition could never reach. Each answer we discover generates 10 new, even more fascinating questions. Each mystery we uncover reveals even greater mysteries waiting on the horizons of knowledge. And this never-ending journey of discovery, this eternal quest to understand the cosmos and our place in it, is perhaps the grandest adventure human consciousness can undertake. So keep asking why. Keep questioning. Given the obvious, continue to marvel at the fact that you exist in a universe where absolutely nothing can sit still, where everything is in eternal motion from the smallest quantum fluctuations to the largest cosmic structures, because it is this insatiable curiosity, this need to understand that makes us truly human, truly alive, truly worthy of being part of this magnificent cosmic dance we call the universe.